we present AnnotateGPT, designing human-AI collaboration in pen-based document annotation. Annotating is an age-old practice that involves making markings on a document to make sense of text. It is a routine part of reading and reviewing, guiding attention, aiding memory, and recording reflections. Nowadays, digital annotation tools facilitate the annotation process. There's a lot of research on digital annotation tools, but here are some examples. Let's start with the standard interface. An annotation can be made by selecting a piece of text and highlighting it. You can also attach a comment to an annotation by typing in the input box. However, this interface is not optimal for a pen-based device, as the pen must target small words and can be a hassle to use. An alternative way to make annotations is to use free-form digital ink, which provides a much more natural experience, similar to what you have on paper. We can also add enhanced features on top of the standard interface, making annotations interactive and actionable. One notable early example is Exlibris, which can gather relevant content from your annotations. The mark parser, which summarizes the number of annotations that you made on the document. And meditation, which supports automatic annotations for poetry. However, a common limitation is that they cannot fully implicitly interpret the annotations, meaning they rely only on heuristic pattern matching and are unable to infer the purpose of the annotations beyond their predefined context. This is where LLMs come into play. They have extensive knowledge across multiple domains and enable human-AI collaboration. Our goal is to explore how annotations support and enable human-AI communication. To frame this in a practical context, we chose a specific domain of student feedback. Because annotation enhances the student-centered approach to learning, it is important by students, but it's a different form of feedback, and it's also vital that annotations are used and received appropriately. Yet this practice is constrained by three recurring problems. First, there are some inconsistencies in quality leading to uneven depth, tone, and usefulness. Second, legibility, where annotations can be difficult to read and interpret. And finally, time, which limits the ability to provide detailed, high-quality feedback. These issues are interrelated. Time pressure leads to rushed annotations, which affects both legibility and tone. Poor readability makes feedback hard to use and inconsistent. Together, these factors limit the effectiveness of handwritten feedback. Now we introduce AnnotateGPT, which addresses these challenges and prior annotation tool gaps, while still giving users full control over their feedback through their own annotations. The user can annotate just as you would on a standard interface. Behind the scenes, AnnotateGPT clusters each pen stroke to associate annotations on the document. Each cluster, or annotation, is assigned an assistant marker that the user can activate by tapping on the annotation. AnnotateGPT will infer the annotation's purpose from its history and the image, and output 4 guesses. Once the user picks a guess, AnnotateGPT stores it for future inferences and annotates the document based on the picked purpose. The annotations generated will be displayed in yellow highlights. Although we chose a specific domain, the clustering and purpose difference are domain independent. This framework can be applied to other domains by manually supplying a different prompt to an annotation module or by having a sub-agent create the prompt. Here is a demo of AnnotateGPT, implemented as a web application for marking English essays. The user first annotates the document. Then, to invoke AI assistance, taps the annotation with their finger. An assistant marker will open a UI which serves an entry point to the AI. The system will display 4 guesses, and the user can hover over them to see more details about each guess. If unsatisfied, the user can also type their own purpose. Once the user selects a purpose, AnnotateGPT will expand on it and generate additional annotations highlighted in yellow. The user can tap on the yellow highlights to read the associated feedback. The user can also accept the annotation or reject the annotation. The user can also comment and continue AnnotateGPT's feedback. There's also a third rating, helpful, if it does not match the purpose but still provides good feedback. To evaluate AnnotateGPT, we conducted a comparative user study to explore how annotations facilitate human-AI communication in practice, specifically in student feedback. The user study involved 2 techniques, AnnotateGPT and a baseline with digital ink only, which is AnnotateGPT without the assistant marker. We recruited 12 teachers from our institution's Faculty of Education, and their task was to provide feedback on an English test from the ETS corpus of non-native written English, which consists of 8 questions. They must rate the annotations, and they have 30 minutes to do so. Participants weren't required to grade all questions, as our priority was to evaluate task performance rather than task completion. A variety of annotations were observed and can be grouped into 2 dimensions: purpose and form. Purpose ranges from micro, which targets fine-grained textual features like grammar, to macro, which targets broader aspects of text like organization and coherence. The second dimension, form, ranges from telegraphic, whether the annotations are personal opaque codings, to explicit, whether the annotations convey clear meaning, usually accompanied by textual feedback. Here are the number of times each type has been observed. At the baseline, participants tended to make more sentence structure annotations. A similar distribution observed for user-authored annotations in AnnotateGPT. However, participants tend to use AnnotateGPT for organization and coherence, where 25 out of 26 annotations were used for it. This suggests that AnnotateGPT encourages participants to address higher-level aspects of the writing. Regarding form, telegraphic annotations were more frequent with AnnotateGPT than at the baseline, suggesting that participants engaged less deeply with the text. Here is an example of P1's annotations. You can see that for the baseline, their annotations are usually accompanied by textual feedback, whereas for AnnotateGPT, the feedback is absent and only highlights are used. The same applies to P4, where only circles are used, and P6, which shows minimal feedback compared to the baseline. This suggests that participants are relying on AnnotateGPT to produce fuller comments while providing very little explicit textual feedback themselves. As previously shown by the number of observations, AnnotateGPT generates significantly more annotations. However, a common theme in the differences between the technique is that the baseline only identifies the problem, while AnnotateGPT explicitly explains the reason. This suggests that AnnotateGPT provides more in-depth and articulate feedback than the baseline. Several implications can be drawn from the study. First, AnnotateGPT served as a cognitive partner, with participants often relying on it to extrapolate from little to no textual signals. This aligns with previous research on LM-integrated systems, where participants shift their focus to identifying issues and having the AI produce detailed responses and format them as well. This also affects educational equity, as teaching quality varies. For example, in under-resourced classrooms, teachers can use AnnotateGPT for clear, timely, and effective feedback. It may also help fill knowledge gaps and level the playing field. But concerns exist about over-reliance, which can promote cultural bias and diminish the educator's voice. Several methods can be applied to avoid over-reliance. While our method embeds AI with manual control via annotations to mitigate this, participants tended to use telegraphic feedback. Lightweight behavioral metrics such as annotation density and duration can help detect disengagement and prompt more deliberate input. We also propose structured sequencing that encourages manual annotation before AI feedback to sustain reflection and maintain user agency. Lastly, our study emphasizes annotation as a key component, not just as a tool, but as an interaction paradigm for engaging with AI systems. Annotations become a shared language between humans and AI, opening a promising design space for interaction. Their in-situ nature makes them especially valuable in contexts where explicit input is costly or disruptive. For example, annotations can be used to edit generative content. A scribble can indicate where an object should appear, mark a sequence in a video, or specify elements directly within the interface to guide AI interaction. Compared to repeated prompting, annotations provide a low-friction way to guide AI. We can also use annotations to annotate the world. While LLMs can process images and live video, users are often limited to voice or text, which can be slow or disruptive. On-screen annotations offer a discrete alternative. For example, translating an item on a menu, saving a photo for later use, or checking which apples are best for making pie. However, these 2 examples are speculative. Future work should evaluate their practicality, user acceptance, and integration with domain-specific workflows. To summarize, we designed AnnotateGPT to support annotation-driven human-AI interaction by exploring annotations as a medium for human-AI communication, and examine how AI expands and elaborates on user annotations, and evaluating user workflows and user experience in essay feedback. Future work can explore annotation-driven intent-aware interface beyond education. Please refer to our paper for more details.